and I will project my screen in a minute, but just to remind you, when I write on the board, I will stop sharing so that you can see the board behind me, and you can go to the view button all the way up to the right of the screen, and then you can change it to speaker view. So then you'll have just this or me on your screen, so you can see better the backboard. Yeah. Okay, I will start sharing then. Okay. All right, so I'm not sure.
Ma'am,
Yes?
you're in the view, like the presenter view again.
Mm-hmm. Is that better?
Yes.
Okay. All right, so I don't know if you guys looked at this, but I would like us to solve this dilution problem together. You will be doing dilution in the lab next week, so it will be good to practice. And also it's good to think about when you have a very concentrated stock solution, sometimes it's really, you need to do step dilution. So this is an example where you probably want to do a step dilution. But before you do a step dilution, let's try to figure out how much we need to get out of this concentrated solution or stock solution to make those, to prepare those different diluted solutions. So what you have here is we want to measure anthocyanins in raspberry juice, and you want to prepare 2 milliliter of 4 different concentration and the 0. That means you're blank. So you want to prepare 0, which is the blank, 0.1, 0.2, 0.3, and 0.5 milligram per ml. So that's your last or final unit. It's in milligram per ml, and you're given a stock solution of 16%. And you want to prepare the 2 ml of each of these different standard concentrations, starting with that 16%. So my unit here is percent, which is grams per 100 ml. However, the final unit that you want is milligram per ml. So the very first thing you do in any calculations, you want to unify your units. That's the first thing you want to start doing. So you look at your 16% and I go, okay, how I can convert that to milligram per ml. Can you take that first step? And if you have an answer, if you already solved it, just either type in your answer or here you can say it. I'll say your name so you can get the participation credit. I'll give you a couple of minutes in case you have not tried it at home, but if you did and you have an answer, please share with the group. So what we're solving it step by step. So what we're trying to do right now is just convert and unify the units. Okay. 160 milligram per ml is the answer. That is correct. Thank you, Jean. So let's see how do we approach that? I'm going to stop sharing. Put me as speaker view. I don't know why it's showing Rachel as speaker view. Why is showing that? You can do it on your own, I think. I don't know. Anyway, so you have 16%. So that's equal 16 grams per 100 ml. So I need to convert 16 grams to milligrams. So in 1 gram, how many milligrams there are? 1,000. So basically I'm multiplying this by 1,000. So 16,000 milligrams in 100 ml. So if I need to get it in 1 ml, so I'm going to divide by 100, and then it's 160 milligrams per 100 ml. Okay, so this is my starting solution. And let's say I want to get the 0.1 milligram per ml, and I want to prepare 2 mLs. So if I start with this concentrated solution, then I'm going to say, okay, so 160 milligrams per 100 ml times X milliliter would be equal to, I want to get 2 ml of 0.1 milligrams per ml. Okay. So if I solve this, what do I get? So the XML equal 0.2 milligrams over 160 milligrams per ml, okay? Because I just canceled these units here. And then you cancel these units and this goes up. So what's 0.2 divided by 160? Does anybody have this answer? 0.00125 milliliters.
Who said that, Pam?
Huh?
Who said that?
Missy. Michelle did? Ah, sorry, Michelle did. Okay, they're sitting behind each other. That's why I got confused. All right. So this, I want to convert it to microliters because in the lab you can, work with microliters in terms of volumes. So 1 ml is 1,000 microliters. So I would move the decimal point 3 places. 0.125 microliters. Okay, this is not reasonable. I don't have a tool in the lab that can withdraw 0.125 microliters. And anyway, it's less than a drop. So it's not really feasible. So I'm starting with really concentrated solution and I want tiny bit of it. Okay, I can't work like that. So I need to do a step dilution. That means I need to dilute this even further, like at least one step before taking it to the next step. So if you all got this, I'm going to erase it. Anybody wants me to keep it longer? Yeah? Why did I divide by 160? Oh, I was just solving for the X here because concentration times volume equal concentration times volume to get how many ml I want from the concentrated solution to prepare 2 ml of the diluted solution. So, and then it's just a matter of solving for X. Okay, can I erase that now? All right, so this is not reasonable. I can't do that, but you have to calculate it first to see if it is feasible. So it's not. So I want to do a step dilution. I want to make it more reasonable. So I would go, okay, let me try diluting this 100 times first. That means instead of having 160 milligram per ml, sorry, this is 1 ml. Sorry, I confused you here. This is 1 ml. Divided by 100, divided by 100. So 160 milligrams per 1 ml. So if I want to dilute 100 times, that means I want to prepare 1.6 milligrams per 1 ml. 100 times. So making it less by 100 times concentration. So I want to prepare this from this. And I want to prepare, say, 10 ml. Why do I say 10 ml? I want to prepare enough stock so that I can prepare different dilutions. So I'll prepare 10 ml of this diluted solution. How much do I need from the 160 milligram per 1 ml to do that? So I do the math and solve for X. In this case, X is going to be 0.1 milliliter. After you do the math, after you multiply and correct for your units, you get 0.1 milliliter. So what you need to do is take 0.1 milliliter of the 160 milligrams per 1 ml solution and add to it, I want to make 10 ml. So if I take 0.1 ml, which is equivalent to 100 microliters. You can easily get 100 microliters using a 100 microliter pipette, mechanical pipette, or a 200 microliter mechanical pipette, and you dial it down to 100. You'll be working with such pipettes in the lab. So you take 100 microliter of your stock solution, and to make it up to 10 ml, you add basically 9 milliliters of water plus 900 microliters of water. You can just say 9,900 microliters of DDW, of distilled water, deionized distilled water, or double distilled water. So you can use a mechanical pipette that is that can give you 5 milliliters, and then you can dial it to 5 milliliter and then dial it to 4.9 milliliters and dispense. You can do that. So, and then you have this solution. And now from this solution, you want to determine, okay, how much I need of this solution, my diluted one that already in 10 ml. How much do I need to prepare 0.1? 2 milliliters of 0.1. So I need 0.1 milligram per ml now as one of my final standard solution. I need 2 ml of that. And I now want to take it from this first dilution, which is 1.6 milligram per ml. I already prepared it. How much of that I need to take to prepare my 2 ml of the 0.1 milligram. So then I'll do the math. So I'll solve for X. So here you would have 0.2 milligrams divided by 1.6 milligram per ml. Cancel your units. And then the ml goes up. So 0.2 divided by 1.6, what would it be? Huh? 0.125.
Hey, Pam, who said that? And also, we can't see you writing down there. You might have to tilt your computer screen down a little bit.
Is that better?
Yes. And then Jean asked, why did you use 9 milliliters? And then I don't know who answered the last question in class.
It's not 9 milliliters. I was just breaking it down. It's supposed to be 9.9 milliliters, which is equivalent to 9,900 microliters. And that you add to 100 microliters to make that solution, because you want to prepare 10 ml of a diluted solution. That means you need to take 0.1 ml from the concentrated solution. 0.1 ml is equal 100 microliters. The rest to get to 10 ml will be water. And that would be 9.9 milliliters or 9,900 microliters. And Chrissy answered the question, the last question. And can everybody see now? Yes?
Yes.
Okay, good. So 0.125 milliliter is equivalent to 125 microliter. So we just divide, multiply by 1,000, remove the decimal point. So 125 microliter is also very easy to get using a mechanical pipette that has a 200 microliter capacity, for example. So you would take this 125 microliters, you want to make it to 2 ml, right? You're preparing it 2 ml. So you take 125 microliters of your 1.6 milligram solution, milligram per mil solution, and then you just add, so that would be 1 milliliter plus 875. So 1.875 milliliters of DDW. This brings you to 2 ml. So 1 ml, so you can take the 1 ml pipette, mechanical pipette, take out 1 ml, add it to 125, and then dial it down to 0.875 and get 0.875 milliliters and add it. So these two will add up to your 2 ml. You'll do the same calculation to get 0.2, 0.3, and 0.5. So basically you apply this equation here, and then instead of 0.1, you do your 0.2, 0.3, and 0.5. You'll be doing similar calculations for the caffeine standards in lab next week. Any questions about this from the Zoom folks and from here?
Yes. Why wouldn't you use a serial dilution?
That's the serial dilution. This is it. We did the first dilution. And from the first dilution, we took the next dilution. That's what we call stepwise or serial dilution. All right. Any other clarification? Okay. Yeah. Yeah, so Aaron is asking if DDW is water. Yeah, we call it DDW sometimes because it is double distilled water or deionized distilled water. We always in the lab use water that the minerals have been removed from it. Okay. All right. So if no other questions, I'm just going to share my screen again. Am I sharing the right screen now, Rachel?
Yes, you are.
Okay, thank you. All right, so this is the calculation. This is exactly what we have just calculated. So you can see here, the final volume is 125 microliters to prepare the 0.1. And then you just do the math for the rest. Okay? If you want to take a picture of it, do, and then anyway, this is recorded. When you go back to the recorded lecture, you'll find it there. Okay. Yeah, yes. What's that? Yes.
So when we plug the 0.2, 0.3, 0.5 into that equation,
Yes,
that number is gonna change,
exactly.
because we're gonna subtract that
From 2 mil. Exactly. So Holland is asking if that 1.875 milliliter will change. Yes, because this is basically your 2 ml minus whatever the volume is from your diluted stock solution. So if you, for the rest, you have 250 microliters, so then that would be 1.75. And then when it's 375, again, whatever the map is, the difference of the two. Yeah. Okay, so the last thing I want to talk about in terms of calculations and
Hey,
preparation.
Pam,
Yeah.
we have a question. How do you know to dilute the stock solution 100 times?
Yes. Okay, so let me go. The trick is, so if we look here, it would be 1.25 microliters, which is a very, very small amount. So 1.25 microliters is very small amount. I think, okay, which is the amount that I would be comfortable with? I thought it would be 125 microliter I would be comfortable with, better than 12.5. You could have done 12.5, but I would have preferred 1.125 microliter, which is 100 times more than this. So that's where the 100 came from. Right? So instead of working with 1.525 microliters, I wanted to work with 125 microliters. I'm more comfortable with that. So I multiplied that number by 100. This means I needed 100 times more dilute sample so that I can take 125 microliters. That's where the 100 came from. Is that clear? Any other question? Okay, good. So moving into buffer. So a buffer, we said last time, is a reagent that we use to stabilize the pH of our medium, whether we are using a medium for incubation or whether we are using a medium for a certain reaction. We don't want anything to the pH to change during the reaction or during the storage or during the incubation. So, and sometimes reactions cause the pH to go down or pH to go up. So the buffer prevent that from happening. So that's why we need to use buffers in our experiments sometimes. And the creation of buffer, or the buffer, is basically a mixture of a weak acid and its conjugate base. So the conjugate base, as I said last time, is basically your dissociated acid or the salt form of your dissociated acid. So here, the acid has a proton, that means has its hydrogen. And when it gives out its hydrogen, it becomes a conjugate base or a salt. Okay, so there's the protonated form and the dissociated form. The protonated form, that means it's the acid that is not dissociated and has its proton ready to give it if needed. And the dissociated form is the form that has no proton and ready to take on a proton. So the presence of both is very important. Why? Let's say that the reaction is changing and it's becoming more acidic. That means there are more free protons in the reaction medium. So if you have a salt in there or a conjugate base, it's going to capture those additional protons and stabilize the pH. The opposite is true. If something is happening and now you have, let's say, OHs, OH minuses in the system, then the acid will give up its proton to resist any increase in the pH. So the presence of both the dissociated form and the non-dissociated form, the dissociated form is called conjugate base or salt, and the undissociated form is your acid, the protonated acid. So the presence of both help with resistance of pH change. One is going to capture any protons coming in, and one is going to release a proton when needed to prevent an increase in the pH or a decrease in the pH. So this is illustrated in the Henderson-Hasselbalch equation, and you'll be using that in the lab to produce a buffer at a specific concentration and a specific pH. So when you have the concentration of the conjugate base equal the concentration of your acid, non-dissociated acid, your log of 1 is 0, right? That's math. Log of 1 is 0. Then your pH equal pKa. That means you have the highest buffering capacity. The maximum buffering capacity occurs when pH equals pKa. Sometimes you're asked, what is pKa? pKa simply is the pH at which you have equal concentration of conjugate base and acid. That's your pKa. It's the pH at which you have equal concentration of conjugated base or salt and the acid. Okay. Now let's use this equation, the Henderson-Hasselbalch equation, to produce a buffer. There are multiple ways in which you would be able to produce a buffer, and chapter either 2 or 3 in your lab manual talks about that. And I will show 2 ways of how you approach preparing a buffer. First, let's take a stab at it and see if you remember any of this or you know how you would approach that. So let's see what the given is. The given is you want to prepare a buffer that has a pH of 4.6 for precipitating casein. That's one reason why you want to do that. You want the total concentration of the buffer to be 1 molar. These 2 are very important given. First, the pH. Second, what's the concentration you're after? Your concentration is 1 molar. Okay. You're going to use acetic acid buffer. Why? Because that buffer works in this range of that pH. So I need to prepare a solution or a buffer that has the acid and has the salt in it. So I need the acetic acid and I need the sodium acetate, which is the salt of that acid. So I'm given, this is what I'm given. I'm given a solution of acetic acid that is 3 molar. That's concentrated more than I want. And I'm given a powder. Here's the powder of sodium acetate. Here's the acid. And then I'm told I need to use these 2 to prepare a pH of 4.6 buffer and a 1 molar. Another thing I'm given the molecular weight of the sodium acetate because I needed to calculate to be able to prepare a reagent at a particular concentration. So I need the molecular weight. And then I'm given the dissociation factor of acetic acid. I would be given that, or you would be given the pKa directly. Okay? You will always be given either the dissociation factor or the pKa. And if you're given the dissociation factor, you just need to calculate the pKa, which is using your calculator, negative log the dissociation factor. So you would use these given. So what I'm going to give you is I'm going to walk you through the calculation. So I'll give you step by step what you need to do. The first thing you want to know and write down in front of you is that your final concentration is 1 molar. This is equal the concentration of your conjugate base or salt plus the concentration of your acid. So you want to mix a certain amount of A minus, the conjugate base. Let me just stop sharing so you can see the screen. Okay. You can see here the board I mean. So you want to know how much of this, so you need to know the concentration of this and the concentration of this. That will give me 1 molar and a buffer with a pH of 4.6. Okay. Then I need to know this concentration and this concentration that would equal 1 molar. And next, I want to apply this equation, pH equal pKa plus log A minus over the acid. But if I want to solve for x, let's say A minus is my x, then I would go 1 minus A minus would be equal to the HA. So I will have one factor to solve for. So I would go 1 minus that. So now I will calculate the pKa with the given. I have the pH, which is 4.6. I'll get the log, I'll get the ratio, and then I'll get the concentration of A minus or your conjugate base or salt. Subtract it from 1, and I'll get the concentration of HA. Let's do that together. Take a couple of minutes, and then when you get to the concentration of A minus, let me know. You need your calculator, and you need to know how to use the log function on your calculator. Your phone has it too. If you don't have a calculator, go to the calculator in the phone, flip the phone. It should give you all the functions you need. And type in if you have an answer, or raise your hand here if you have an answer. Okay, we're getting an answer. Huh?
Oh, I was going to say Alaman has an answer.
Yeah, and there was a question from Al. Oh, I answered that question. Okay, so we've gotten an answer for A minus or the conjugate base. So since we've got an answer, I'm gonna go ahead and solve it with you, but either Al or somebody in the room is gonna give me the values for the log because I don't have that right now. So what's the pKa after you apply the equation? Al, you can type it in for me.
The pKa, wait, can you hear me, Pam?
Yes.
Is 4.7595.
Yes, so we can say 4.76. Thank you, Jean, as well. All right, so we have pH 4.6, and the pKa is pH 4.76. And then the log here. All right, so if I bring this over, it would be minus 0.17. Oh, 6, sorry. Just the difference between these two numbers equal the log right, so now what would be, after you do this, what would be this value here? So L or Jean, whoever was solving, what, after you do the log, anti-log, what would be this value? 0.692, okay. All right, now I'm gonna solve for A minus. Just the algebra here. And then you bring it over, so it would be 1.69. So you have 1, and this becomes a plus, so it would be 1.692 A minus equal 0.692. And then for the A minus, you would divide 0.692 by 1.692. What do you get? You get the 0.409 molar, 0.409 molar for the A minus. Then I have this, I will replace it here and get the H. A equal 1 minus 0.409 molar. So that is 0.591 molar. Perfect. So now I know the concentration I want of HA, and I know the concentration I want of the salt. So I solved this part. Now, the second part, okay, if I want this and I want this, and I have the original solutions, I need to know how much of the original solution I need to take to get this concentration, and how much of the other sodium acetate I need to take to get this concentration. So I start with 3 molar, and I want to prepare a liter of my buffer, let's say. So I go, okay, I have 3 molar of acetic acid. How much of that I need to have a 0.591 molar of the acid in 1 liter or 1000 ml. Okay, then I do the math and I get the X milliliter equals, who can do the math for me? 591 divided by 3. Tracy? 197? 197 ml. So I need 197 ml of the stock solution of acetic acid. Perfect, I solved that one. Now I need to see how much I need of sodium acetate powder. Okay, I know from here that I need 0.409 molar. Remember, molarity equals number of moles in a volume, and the volume is a liter. And the number of moles equal mass, this is what I want to solve for, over molecular weight. So the number of moles is 0.049 moles in a liter. Okay? So my number of moles is 0.409 times my molecular weight, which is 82 grams per mole. This is moles here. And then we get the mass. All is going to be in a liter. Okay, so my moles cancel. So what's 82 grams times 0.409?
Jean says 33.5.
And Abby here gave the answer to 33.5 grams. Good, I'm all set. Now I know how much I need of the powder and I know how much I need of the stock solution. All I need to do is prepare that 1 liter of buffer. So what I would do then is I will weigh out 33.5 grams of my sodium acetate, dissolve it in a portion of water, let's say 200 ml of water, 300 ml of water, and then I add to that 197 milliliter of my acid, and then put them in a volumetric flask and make up the volume to a liter using water. And then you have your 1 molar buffer at pH, hopefully 4.6. What we usually do as a last step, and that's what you would do in the lab, is determine the pH of your buffer using a pH meter, which you will do next week, and you'll calibrate the pH meter. You will measure the pH. It should be around 4.6 if you did everything correctly. But it's kind of like, this is theory. You always have to kind of adjust your pH at the end. So you will see if you got a pH of 4.5, 4.7, then you use a concentrated base or a concentrated acid to just adjust the pH to exactly 4.6. And that's what you will be doing. Now, there is another way to determine how to prepare this buffer. And I'm gonna give it to you. And then it's up to you which one you would prefer when you're actually going to prepare a buffer. So this other method is actually my favorite method, my preferred method, but that's only me. But both are correct. So I will start sharing again my screen. This is the calculation that we just gone through, and you'll find it when you watch, it's in the recording, so you will find that there. So it's exactly what I went over just now with you. Now, the other method of determining how much you need of each is, in my mind, simpler. So I would prepare 1 molar solution of acetic acid and 1 molar solution of sodium acetate, then determine how much I need into only volume, how much milliliter I need of each to mix together. So I would prepare a liter of each at 1 molar concentration, and then determine how much I need this stays the same here. So what was the value of this? What was it? It's the same, 0.69, okay. 0.692. That's the ratio. I will need that for later. So that's good. Equal A minus. I need the same value. So in this case, instead of saying 1 molar, I will say this is a volume and a volume in milliliter.
Hey, Pam, we can't see the board.
Oh. So here, instead of 1 molar, I'm going to say I want to prepare 1,000 milliliter of 2 solutions mixed together, but all of them are at the same 1 molar concentration. So in this case, I'm going to say I want to prepare 1 molar of acetic acid and 1 molar sodium acetate powder. So 1 molar of acetic acid, if I want to prepare a liter of that, I'm going to say I'm going to prepare 1 molar acetic acid and a liter of it, starting with 3 molar, and I want to know how much I need to take of that. So if I solve this, it would be 3.3 milliliters. Right? So 1,000 divided by 3 is 333 milliliters. So I would take 333.3 milliliters of my concentrated acid, add water to it. So that's 666.7 milliliter water. And then I get 1 molar acid. 1 liter of 1 molar acid. Good, I have that first one. Now I want to prepare a liter of the sodium acetate powder at 1 molar. So here my molarity is 1, number of moles is 1 moles per liter, because I'm preparing a liter. And then again, 82, no, I'm solving for the mass. So mass in grams over 82 grams per mole, my molecular weight. So I need to weigh out 82 grams. Okay, so that goes here, 82 grams. So I need 82 grams in 1 liter of water. You make up to 1 liter in a volume. So you usually solubilize 82 grams in a little bit of water, 200, 300, 400, whatever. And once it's soluble, you put it in a volumetric flask and you make up to that 1 liter. So you get 1 molar salt. You get 1 liter of 1 molar salt. Great. So now you have 2 solutions at the same concentration. Now all you need to know how much of each, how many milliliters of each to make up to 1,000 milliliters. Great. So when I get this value, the 0.692, which is the ratio, this value here, I would, instead of 1 for the concentration, I would put the 1,000 ml here. Okay, let me write it clear. So instead of 1 minus, I have 1,000 ml, I will put 1,000 ml minus the A minus. And then I use my algebra and solve for A minus. Can somebody tell me what the A minus is here by solving this equation? Just do the math here to get the A minus. Holly, you have a? No? It's basically 692 would be equal to, let me write it out. So 692 minus will be equal to actually 1.692 A minus. So 692 divided by 1.692, what do we get? Huh? 408? So 409.
Pam, who was that?
Anastasia. 409 milliliter of A minus. And then HA would be 1,000 minus the 409, which would be the 591 milliliters. So basically, I get 409 milliliters of my salt solution, and I add 591 milliliter of my acid solution, both prepared now at 1 molar. Mix them together, I get 1 liter of 1 molar buffer. Look at the pH, adjust the pH, and voila, you're done. So what I want to say is, let me share my a minute here. Let me share my screen. So that's the other way we just solved it. Well, I have here 408, and so it depends on your math and your rounding. 408, 592. So it depends on what you use, decimal points. But anyway, so you would add the 408 to the 592 milliliters, and you get your 1 liter. So that's exactly how we just solve it here. So for your lab on Monday, here's the thing. We have the pre-lab quiz. So you're going to solve the pre-lab quiz. Everything you solve are the calculations you need to actually prepare your reagents in the lab. So what we'll do in the lab on Monday is go through and make sure you've done the correct calculations that will get you to prepare your reagents. We already have videos for you for instructions. I gave a very short introduction, 8 minutes. And then Cindy has introductions for every instructions how to produce every reagent. So please review those videos. They are under media gallery, I believe. And I will post everything you need to have for the lab today on Canvas, and then I'll send you an email reminder. I would like you to please read or review lab manual chapters 2 and 3. They have the background information for calculations. Review the lecture and all of your calculations. You have a lab addendum for this lab. That means we have the instruction for the lab on Canvas. So make sure you either print it or have it in front of you during the lab. And you will have a pre-lab quiz to complete, and you'll do all the calculations during the weekend, and then bring it with you for the lab to go over together. One thing I would add, if you're able to come to lab on Monday 10 minutes early or so, that would be helpful, because we want to go through your lab notebooks and review calculations with you and then get you started. Anything else, I will send you a reminder in the email. Let me see.
Hey, Pam,
Yeah?
for their work from today, for extra, do they turn it into the extra credit 923 on Canvas, or will there be another Dropbox for today's work?
Today's work is combined with Wednesday. So on your piece of paper that you started on Wednesday, please complete whatever we went over together today. I would like to see complete calculations. And then you can take a picture of that and upload it. There should be a place on assignment for today to upload, I believe by 5 p.m. I don't know if Laura's here to confirm, but I think.
Yes, Pam, I had it for 5 p.m. tonight. Do you want me to keep that deadline given that they're adding more work from today?
Maybe we can do it by 5 p.m. on Monday.
I can do that. I'll change it.
Yes, so we'll give them extra time. And again, there's no obligation. This is extra credit, but it would be good to submit it for 5 extra points. All right, thank you, everybody. Have a great weekend. Yes, I will put my mask on and make sure I stop recording.